Well, hello and welcome back to Gearhead Geeks, where in this video we are going to be exploring the geek part of Gearhead Geeks. We have a problem. The problem is that on this KZ400 we have put a tack on it, and the tack had really no specification sheet. It says, oh yeah, it just works with all motorcycles, yada yada. Well, come to find out that it doesn't. It is designed to work on a bike where the points are on the camshaft. Well, on the KZ400, the points are on the crankshaft. So every time the engine spins over, we get a pulse or something going to the coil. And that's happening twice as fast as it would on the camshaft. So what happens is this tack is reading at twice at what it should be. If you're at 1500 RPMs, it's reading 3000. So how do we fix that? Well, we could go buy another tack and it works off that, but then some of those tacks are not what we need or whatever. So let's make what we have work. So what we're going to do is we're going to geek out a bit, and we're going to go in and start talking about making an electronic divide by 2, which means every pulse that comes in is going to be divided by 2. So we get back to the number of pulses needed to get the tack to work. So how are we going to do that? Well, I'm going to show you. I'm going to explain how a certain chip works, and we will then go in and explore it, and then we'll actually build it and use it. So to start off with, we already know the problem. So how do we fix that? Well, what we're going to do is we are going to use a chip. There's going to be some resistors and some other pieces here, but the chip is called a CD4013, and that is what's called a D-type flip-flop. That D-type flip-flop is a device that has two outputs that are the opposite of each other. So what I'm going to do here is I'm going to go with a whiteboard, and we'll explain what the chip does and then how we're going to use it. So off to the whiteboard. Okay, so what we have here is we are going to be using a chip that is called this D-type flip-flop. So we'll draw that, and I'll explain how it works and what some of the nomenclature is. Okay, this is the schematic of a D-type flip-flop. So what really happens is that in briefly, that there are two outputs here. There's a Q and a not Q. What these are opposite type outputs. Q is when this one is at a high level, the not Q will be at a low level. When the Q is at a low level, the not Q will be at a high level. So let's talk about levels and edges, because we have to understand a little bit about how edges and things work when we're using a flip-flop or this particular device. So if we were to start out, and I'll just draw a little bit. What we have here are what we call levels. This is a level, this is a low level, and this is a high level. Easy enough. This is, in our case, would be 12 volts and 0 volts. So this is 0 and this is 12. Okay. With that being said, there's other types. It's called edges. Okay. And we have edges. And edges, This is a rising edge because we go from a 0 to a 1, and this is a falling edge when we go from 12 volts to 0 volts. So we have edges and we have levels, and that's really all we need to know about this. So with that being said, how does this guy work? Well, this guy here, the 4013, he works off of edges. So what he does is every time the edge changes from low to high on what they call a rising edge, this device will look at whatever is here on the D pin, which is data, if this is a high or low, and it will put it out to the Q. Now, so what ends up happening is when this rises, if this is low, sitting at a low level, and this is at a high level, and this rising edge happens, what will happen is when it's presented here, this will change to whatever this is. It kind of latches in. Then what ends up happening is it goes low, and if it goes high again and this is still high, this stays high, it doesn't do anything. But if this changes to a low level and it goes high again, it will change to a low level. So it presents whatever's here, here. Well, now what we can do to get the divide by 2 out of this is fairly simple. What we'll do is we start out in life with, what we'll do is we'll take this and we're going to hook this guy directly to this guy. So this is the opposite of this, and this is our data pin. So what ends up happening here is this guy is sitting at a low level at the moment. That's 0 volts. This is how it starts out. Here, we'll draw it over here because we'll be doing some more drawing here. We are starting out at a low level, and we go high. And what happens here is when we get this rising edge, this is when the points break, because the points are at ground right now. And then when the points break, we're hooked up right to the points. It goes high because as soon as it opens up, it gets current back through from the coil, and this will rise high. Okay, so this is a rising edge. And so this rising edge, this is event number 1. We'll call those rising edges events. As we move along, matter of fact, we'll just go on ahead and draw the whole, what it would look like. And I'll explain as we go along. And et cetera, et cetera. And this is what is happening on this pin right here. We're going to go right to this pin. Okay, so this is event number 1. This is a rising edge. Then the points are open, then the points close, and this is event number 2 where the points open, and event number 3 where the points open, event number 4 where the points open, and event number 5, and so on. So what happens here is now we're looking at this clock and we're looking at this data. Let me draw the D better. Okay, and we started out with 0. We just turned on the bike. There it is. This is at 0. We haven't had any rising edges. We haven't had anything. So finally, we get to a point where the bike is starting to go, and we get a rising edge. That means the points have opened. Okay, so now we see this, and what's happened here is if this one was low, this one would be high. Okay, so this is at 12 volts, this is at 0 volts, because remember, they're always the opposite. So this is high, and it's hooked to our data. It sees this rising edge, and all of a sudden, this guy pops up, and he goes to 12 volts. All right, so this happened on event number 1. that happened, this goes on, and that popped up. So now what's happened is as soon as this went up, this one went down. So now this is at low level, so this is at 0 volts, just 0. And so we're going along over here, and the points are open, then the points close, all right? And then the points now go across, and now the points open again. This is event number 2, and it comes over here, and it looks, and it says, oh, wait a minute, this is a low now, because we've gone back to low, this was high. So then what ends up happening on event number 2, this goes low. Okay, so what's happened here is we now have our event number 2, and I should draw it a little bit different here. Let me just draw it a little bit different. It's a little longer, because what's happened here is this has gone high, it's gone low, and it's finally gone high again. So that takes a little longer. And this one has now dropped low on event number 2, okay, because this was low. Then what ends up happening is this output right here goes high again, because this one's low. Let me draw it in the right spot. Okay, this one's low, so this one now goes high. And we'll just kind of draw that the way it did. Then, so now we are high again, and event number 3 comes along, and guess what? We are closed, and then it opens again, and instead of it going high at the same time or whatever it's going to be, this one here is sitting here high. Well, excuse me, instead of it going low for each one of those, this one here is now sitting high. So this is high. So event number 3 makes us go high again. And so on and so forth. And what's happened here is all these events. So event number 1, instead of it went high here, and then event number 2 would have gone high. Look what happened at event number 2. It went low. And then event number 3, it went high. And then, so when it goes high, now this has gone low again. This has gone to a low. And RD is at a low. Oops, excuse me. RD is at a low. So event number 4 comes along, and this rising edge, and guess what? It goes low. So instead of it going high at each of these events, it's going high and then low and then high and then low, and then event number 4 would come along while this is high, because when this switched to low, this went to high again, and so on and so forth. It just goes off and does it. So what we do is we're dividing down each of these pulses, and that's basically all that happens here. So to make all this work, we got to put some circuitry in there, and I'll go briefly on that. I know it's a little bit much, but we get the idea. So what we have to do is on this, we're going to put a resistor in here, and that's the symbol for a resistor. And then, now let me move this out a little bit. We'll put a resistor in there. Okay, and this is going to go to our points. And then I'm going to put some conditioning in here. I'm going to put a diode in here that is a transient voltage suppressor. And what that does is it clamps down any weird voltages, because when a coil charges and discharges, especially at those points, the coil is kind of trying to discharge back through those points, and you can have transient voltage spikes, and this little diode will kind of clamp those down and keep it from destroying this chip. Okay, this is nothing more than the output to the tach. That's all that it is. This will go out to the tach, because we've been dividing them down as we go through, so the tach should run at half the speed of this, and hopefully that cures our problem. We also have to hook up some stuff. So this is pin 14, and this goes to 12 volts. And this is pin 7, and this goes to 0. And there's a set and a reset, which is pin 4 and 6, and they will all go to ground. So that is how it gets hooked up. The 4013 actually has 2 of these inside of it, but we're only going to use the one. So this gets hooked to here. We hook these pins to ground. We have to make a wire coming out to the tach. We have to get a wire coming out so we can grab 12 volts. We also have to have a wire coming out so we can grab ground. And then we have to have a wire coming out here so that we can put our resistor on and our transient voltage diode on there. And the whole thing should work perfectly. So I'm going to go on ahead and build this, and we'll look at that and give it a try and see what it does. I could use the experimenter's board and try it, but I have confidence it'll just work. So here's what we're going to end up doing. We have a little anti-static mat, which is you should use whenever you're building these types of things. We have our CD 4013 chip, which is what we're going to use, but we're also going to take that, we're going to use a socket on this board so that we can pull the chip out and put it back in case something bad happens. We can replace the chip without too much issue. And what we also have here is a bit of what they call breadboard. Now, there's different types of breadboard that you can get. As you can see, it's got a bunch of holes in here, and they actually are the right spacing to accept these chips and the sockets and whatnot. And on the other side, there are pads, and you can solder onto these pads. So it allows you to go on ahead and put in a socket or a chip or a device or whatever you're going to be doing and be able to solder onto something. So you're, instead of just trying to solder onto the wires and whatnot, because that can be problematic. So what we're going to be doing here is we're going to be taking and soldering on the chip, and then we'll be going on ahead and using this resistor. This is what the resistor I showed you in the drawing. This is a 10K resistor. Its marking are brown, black, orange, and the brown means 1, the black means 0, and the orange means 3. Excuse me. And so you take that and you have a 1, 0, and 3 more zeros, and that gives you 10,000 ohms. That's what we want. 10,000 ohms, a 10K resistor is used a lot in electronics. It's a good amount of resistance, but it still lets enough current flow through to do its job. This is our transient voltage suppressor. The bad part about this is that it is what's called a surface mount device. It doesn't have any pins in it. So those pins, excuse me, all right, let me get so you can see it. It's just a little guy, and it's still in its wrapper. It doesn't have any pins on it, and with no pins on it, it is really hard to mount onto this stuff. But we'll just get something sticking out, and we'll do it. That's because it's what I've got. We're doing things with what I already have. So first things first, what you do is we probably won't be using this whole board. I might cut it off a little bit when we're all done. But at the moment, what we need to do is get our socket about centered. And the reason I'm centering it in here is because we need to be able to have wires and stuff coming out of it. So we don't want to have it on the edge where we don't have any room to work or put anything on there. So I'm going to go on ahead and get this in there. And these sockets can be a little fiddly going in. It just takes a little bit of doing. Okay, the socket is in. It's on the board. We are going to flip it over, and we are going to solder it in. We can solder all the pins down, and it'll be fine. You don't have to do anything else. This is a temperature controlled soldering iron. In this particular case, it's about 470 degrees. It's going to melt fairly quickly. This is just plain old solder. as we go in. And it's a little hard to see, so I'm going to do the best I can here to do this so you can also see. But we'll melt a little solder onto that guy, and we'll melt a little solder onto that one. And let me see if I can find the other ones. Okay, we'll go to the other corner, melt a little bit on that one, and that helps us see where things are. And we just go through. Now, one of the reasons that a socket is good also when you're doing this is eventually the chips can be sensitive to heat. And you want to make sure that you don't fry that chip. And we'll go on ahead here. And what we do need to do is we're going to be making sure that none of these pins are crossing over each other, because at the moment we're just kind of soldering the socket on there so it doesn't move around. And there is some residue on these pins. I'm not being that careful at the moment. I just want the socket on there. So now this is soldered on there, and it's not looking too bad. Yeah, we're not getting too many crossovers going on. So what we want to do is, we know a few things. We know that pin 1 and pin 2, this is Q and not 2. And so when you're looking at chips, there is a little mark. I don't know if we can bring that in enough to where you can see it, but there's a little mark on top, and well, wherever it is. And then you count the pins: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you go counterclockwise with it. So we know that pin 1 is our Q output. We know that pin 2 is our not Q output. So we also know that, so pin 2 needs to hook to pin 5, and pin 5 is our D output, which is our data on this. So what we need to do is get a wire and hook those two together, but we're not going to do that now. What we want to do is we're going to go to pin 3. Pin 3 here is where this resistor goes. So I could lay the resistor flat in here, and I just have to think about that. But yeah, we'll just go on ahead and lay it flat. So what you want to do here is you fold over your resistor, get it folded over, and we're just going to line it up at pin 3. And the good part is, if you look on the board, you'll see that there's little markings on the board of what the pins are, and that helps us understand so we don't have to count each time. So with this resistor hooked to pin 3, well, it isn't hooked to pin 3, it's lined up at pin 3. What we're going to do is we're going to flop it over, and then what we're going to do is we're going to take it and we're going to solder it to pin 3. And we'll just, are we in the field here? Yeah, you can see it. Let me move this up a little bit. Got to do that. And then we'll just take that and we'll just solder it into pin 3. And I should have enough. Yeah, it's soldered onto pin 3. Then we'll take a small pair of wire cutters and they even say that they're ESD safe, but we're going to take our small wire cutters and we'll take off that pin. Now what we want to do is we want to save these wires, and the reason we want to save these wires is because of the fact we can use them to hook up other stuff. So what's going to end up happening here is we're also going to have to put our transient voltage suppressor into pin 3, but we'll have to figure out how to do that. I haven't quite figured that one out quite yet, because it's got to go between there and ground. So now this is going to be our input. So what we'll end up having is a wire coming in here that will hook to this guy, and that will be where our points come in. Then what we need is we'll have a wire coming out of pin number 1. That will be going out to our tack. So our points coming in, going out to our tack. And then what we'll do is pin 7 in this world goes to ground, and pin 14 goes to ground. So we'll have some wires coming out of those from these sides. I'll just run it over, and we'll just continue on that way. So I'm just going to go on ahead and build this board. So at least you get an idea of what we're trying to build here. And when we're done, we'll be able to take the socket and put this chip, and we'll be able to put it right into the socket. We'll press it in and it'll all be good. So I'm going to go ahead and solder some things together, get it all done, and we'll go from there. So now that we've got our socket soldered in, we've got our 10K resistor soldered in, we need to put some wires on this thing. There's going to be basically 4 wires coming out. We're going to have to pin 14, we are going to have a wire coming out that will be going to 12 volts. Pin 1 is going to have the output to our tach. Pin 3 has our 10K resistor on it, and then there's going to be a wire coming in to that from our points. And pin 7 will go off to ground, and then some other pins hooked to that. So I found some 22 gauge wire. I've got a thing of different colors here, and 22 gauge, and I can strip off the end, and it will fit perfectly into the holes as we need it. So our output in this particular case is going to be yellow, because I believe the tach wire is yellow, and that's good. That's what we want. So I just need to twist this a little bit, and then I can go on ahead and push it through the pinhole. Maybe try and push this through the pinhole. It's a tight fit, so I have to be kind of careful what I do here. And in it goes. So that's perfect. And pin 1 is our output. That is our Q output. And so what I'm going to do here is I'm going to heat up our soldering iron, and somewhere over here I think I have a little soldering perch. I do, right here. And this guy, I can kind of put my wire, get my wire pointed in the right direction, and it will sit in here just like that. Okay. And make sure that we're melting solder properly. So now what I need to do is I'm going to solder this wire in, heat it up very well, and you just have to be careful here because we don't want to bridge off between pin 2 and this wire. Very good. Okay. And you saw that operation, so I'm just going to continue on. I'm going to go on ahead and continue on wiring all this in. We'll get all the wires that are needed in there, and then what we're going to do is we're going to crimp on the proper connectors. I'm going to have to go pull the tank off and make sure what we need here, but we're going to be making some connectors that go from 1 into 2 and things like that. So, and we have all our wires soldered on the way that we need to. I'm going to go through, I got to hook a couple wires across the back to get a couple things hooked up. I need to hook pin 4 to ground, and I need to hook pin 2 and 5 together. So I'll be doing that, and once that's all done, then we can start putting the ends on it and figure out how to get our little transorb on there, and we'll go on ahead and give it a try. So I have gone on ahead and installed all the wires that we're going to need. This is going to be for plus 12. This is going to be our tach signal out. This is our point signal in, and this will be the ground. I haven't put the connectors on them yet. The socket is installed, and I have installed our transient voltage suppressor on the back, and everything is wired in the way it needs to be. It's a little hard to see. This camera doesn't want to like to focus very close, but everything is wired in, and it's very, very solid. I use solid wires to hook everything together so they're vibration proof, and everything is soldered tight onto the board. So the next thing that we have to do is see if it actually works. And the first thing we need to do is, because I put the socket on the board, now I can take the chip. There's a little mark on the top of the chip, and we line that with the socket. There's an indent on the socket, and we just plug it in. And you have to make sure that when you plug in a chip, that you don't fold over any of the pins, or any of the pins are folded out. You make sure that they're all lined up perfectly. So what I need to do here now is we need to get power to this. So I've got a power supply over here, which I haven't really prepared, but we'll get it out. Got a power supply over here, and we can take and we can hook our positive to hit to this, and these leads have been used for plating, but that's okay. They'll work okay. And then what we're going to do here is we'll turn it on, and we'll get our voltage up to about, we'll get our voltage up to, I'm going to set it at 5 because the range of this chip is anywhere from 3 to 16 volts. And I got to set it to 5, and there's a reason for that, and I'll explain. This is an oscilloscope. It's a portable oscilloscope, and it has a bunch of functions in it. And one of the functions that it has is it is a square wave generator, and the square wave is going to simulate our points. So what you need to do with this is we just need to hook the ground side, so the scope has got ground, and then we take our input, which is going to be this blue wire, and we will introduce a square wave into this, and that square wave well, then we can look at the output, but on channel 1, this has got 2 channels, so we'll be able to look at our, so we get everything untangled here, we'll look at our input on channel 1, and that should connect fairly well, and then on channel 2, which is here, and everything is all tangled up because every time I touch anything, I tangle up wires. Channel 2 will be our output. So basically, we'll turn on the scope, and we will then go on ahead and let's go set it. We'll set up so you can see what's going on. It has a signal generator in it, and you set it up to a square wave, and we'll set it at 50% duty cycle. That's fine. 50% duty cycle means it's off, and then off for X amount of time. It goes up, and then it's on for X amount of time. It goes down, and so it's 50% the same exact top and bottom, which is fine. We don't care what it is. The timing of that is unimportant. What we want to do is make sure that the signal coming in is at a certain number of pulses, and the signal going out is half as many pulses. So we'll go back to that. So we've got this done. Okay, and it's a square wave. That's fine. And then we go back to the menu, and then we'll go back to the oscilloscope, and I don't want the menu. I want to go back to the oscilloscope. Okay, so what do we have here? We've got, let's get our voltages right. It looks like our ground is not hooked up here somehow. Let me check that. Let me just, oh yeah, it come disconnected. That's bad. Okay, so now what we need to do is we'll go back to our menu. We are going to go back to here, and we're going to go to our signal generator, and we're going to make this a square wave. That's what we want. Fine. And save that. And square wave. And then we go back to our menu and go back to our oscilloscope. And now we have a square wave going on here, and we still have a bit of a ground problem. But what we're seeing here is our channel 2. Get this channel 2 guy hooked up and get him grounded. And there it is. We just have a bad connection here. Okay, so now, I don't know if we can see this. I hope you can. But what we have here is we have our signal coming in at this frequency. And so we have 1, 2, 3, 4, 5, 6 highs, and now we have 3 highs. So it has divided the signal in half, and that's exactly what we need. So this guy can now, we can put the connectors on this, and it will allow for us to have our frequency divided so our TAC will work, supposedly. Everything looks like it's working okay. The flip-flop is doing the job that it needs to do. We are in good shape. So I will start putting the connectors on this thing so we can get it hooked up to the motorcycle. So now that we have gone on ahead and tested our circuitry, we now need to go on ahead and get wires all set up for plugging into the motorcycle. So the first thing we need to do is we need to get power going into this. This is going to come off our switch power that goes to the coil. This line here will be what goes out to the TAC. So it's just we'll be just putting a female connector on this. It'll go straight out to the TAC. On this one, this is our input, but what we're going to do is we are going to put a male connector on here, and then we're going to build some little pigtails that allow us to plug in and get 1 into 2. So we'll go do that. The first thing we need to do is have a proper crimper. These are crimp over pliers, and I've got some different pieces here for building that stuff. So the first thing is to build those is, here's one thing where we take, and this will give us a double, and then we can take a single. So what that's going to do is, whoops, that's not a single. I gotta get a single here that allows us to take one wire plugging in and be able to get 2 to plug into it. So the first thing we need to do here is on this guy, we need to get something it can plug into. All right, so what we'll do is I've got some other pins in here and whatnot. I'm just going to grab what I have. Make sure that everybody plugs into the right size. So on this one, it is a fairly small wire, so we're going to use, then the way you use these crimpers is pretty simple. You just take them and you go on ahead and you get them lined up inside the crimper. Oops, it's going to work here. Get them lined up inside the crimper, and all that you have to do, and I'm going to take a little insulator on here, which we can do. You then shove the wire into this, and you put it in just to where it's going to crimp over the insulation and then crimp over the wire itself. So you take it and you give it a good squeeze. Okay, and then we'll pop it out of there. And I don't know if you can see this, but what it is the wire is crimped over on the insulator, and it's also crimped over very tightly on the wire itself. This is not coming loose. I am putting a ton of pressure on that, and it's just fine. So step one is done with that. Okay, now the output of this is a female connector because it goes directly out to the tack. The tack has got a male connector on it, so we'll get a female connector. And we've got one right here. Of those. And we'll get a little cover for that, so it covers things over. And again, we take this and we put it into our crimper, get it started. We can now put this in, make sure you got no strands hanging out or doing anything else. And then we are going to make sure that our wire is right into where it crimps over. We're going to give it a good hit. And we pull it off. And again, we check it and make sure it's very, very tight. No ambiguity on that one. Okay, so that will allow us the tack to come in. Now this is going to be to our points. This goes to the same wire as points because that's our input. So this one's going to need a male connector on it. And let's see if this connector is going to work. So we've got all the connectors on our board, and I'm probably going to end up chopping off this board a little bit because we don't need all of this, and we're gonna wrap this thing up. So all these wires will be coming out in one direction, and we'll tie them all up and cut that off, and then we'll build the little pigtails for plugging everything in. Okay, so I've taken a piece of insulated covering, it's just this expandable covering, and covered up the whole board so that it's insulated and there won't be any problems. So next is we'll figure out our ground line. So what I've done here is I have taken and cut down the board and encapsulated the board in some shielding, and this is not electronic shielding. It's just to keep it from anything from shorting out. It's just some wiring loom cover, and it holds onto this real tight. So we have our 4 wires coming out. We have our tachometer input. We have our power, which is hooked to VCC or VDD on this chip. We have our tachometer output, and we have ground. I have taken and put a ground wire onto our frame, onto our coil actually. So I have a ground wire. We have this wire. This is the wire coming up from the points. This wire is our power to our coil, and our coil would actually plugs in here, just like that. So what we want to do here is we are going to take and insert this guy. So what we do is we get our coil wire. This is power to our coil, and in this case we're just going to hook it to our red here. Okay, and then we're going to take and it will now, that's our coil power wire. Then we'll take the power that we need for our little divider. Then we take and we'll plug in the ground. Okay, and this is the wire to the tachometer, which I've got coming down through here. Okay, and the one last one is our point wire coming up. So we're going to take our blue wire, and I've made the double connector here. So this one goes here. That's our point wire. And this one goes here. This goes in. This is where our points would connect into the coil. And this is the input in the blue wire again into our little device. So everybody's hooked up. We have power. We have coil input coming in. Here's our points coming in, going into that. It also goes into here. We have now our tack wire coming out, and we have ground. Everything is hooked up. I'm going to go put everything in and get it all kind of put away in there, so nothing comes out. We got to just make sure things are tucked away. We'll do a little tying on it. Yep. And everything will tuck away in there. Let me put the tank on it, and we'll start it up and see how that goes. And on this bike, I have set everything up so it mounts just like the factory does. It's got a little hook in the back here. The seat can go on. That key in the right direction. This guy basically on there. Snap it down. We're tight. Everything is good. And I'll move the camera over to the other side and start this up. Alright, so that is how, if you have a tachometer that is reading twice as many pulses or twice as high as it should be, that you can make a divider using a CD4013 to take, and instead of having 10 pulses, you get 5. And that basically just works perfectly. We put it in there, plugged it in, it instantly went from 3,000 at, when it was running at about 1,500. The tach is not that accurate on this, but it's close enough. But it was reading double. If you even revved it up, it would be almost all into the red line. Now it's just fine. So whenever you have something like that, you can just use something like this, get that chip for, in essence, I bought that chip in a set, and it probably cost me 20 cents for the chip. I spent $5 or $6 on a whole bunch of extra stuff because I just use that stuff anyway. And making stuff with breadboard is not hard to do. It can be done. So anyway, that's how you do it. You can then, by doing that, you have a divider. It works good. And at least now you can take an inexpensive tack that isn't meant for you and divide it on down, and it works. So thanks for watching. Please don't forget to subscribe, like, please comment. If there's any questions, just put it in the comment and I will answer every single one, every question that I possibly can. Thank you much, and we'll see you next time.